As you said, this talk is Apple's Predicament, NSPredicate exploits on iOS and macOS. My name is Emmitt. I also go by Alkali. All right, let's get into it. A little bit more about me. So I'm currently a vulnerability researcher at Vigilant Labs, though the research for this talk was done while I was at the Trellix Advanced Research Center. I'm also the author of the Radius 2 symbolic execution framework, which uses Radar 2 to quickly and easily perform symbolic execution and taint analysis on binaries from many different architectures. So check that out if it sounds interesting to you. And I'm AlkalineSec on Twitter, I'm at X, and Alkali at InfoSec Exchange on Mastodon. All right, so on the agenda for today, first we're going to talk about why we should care about NSPredicates. And then we're going to cover what an NSPredicate actually is. Then I'll discuss the mitigations that Apple has added to make NSPredicates less powerful and how those could be bypassed. We'll go over some of the vulnerabilities I discovered and exploited in the course of this research. And finally, we'll talk about what can still be done with NSPredicate. All right. So let's talk about where all this sort of began with the forced entry exploit. So I've been obsessed with NSPredicates since I read the second part of Project Zero's blog post about the forced entry attack. So it was an exploit chain targeting iOS that was found in 2021 in the wild. And so their first post covered the iMessage exploit that sent this fake GIF that was actually a PDF, which exploited an integer overflow in the JPEG2 image compression codec. It was this absolutely wild, incredible exploit that used the operations on groups of pixels to create an entire virtual machine. Many of you probably know about it. The ultimate purpose of this virtual machine in this instance was to create and evaluate an NSPredicate, which sent another NSPredicate to an unsandboxed process. So while the iMessage exploit received most of the attention, rightly so, because it was crazy, I was fascinated by the sandbox escape and by these NSPredicates, these powerful little strings that defeated all of iOS security. So why was I so fascinated? The answer is because iOS hacking is hard. It's very hard. And the reason why is they have common mitigations like ASLR, address space layout randomization, though in the case of iOS, the ASLR is a little bit limited, which we'll get to later. But more importantly, iOS has other less common measures, like strict code signing, which prevents any dynamically generated code from being executed. Only code signed with an Apple-approved certificate can run on these devices in their normal form of operation, and every other form of scripting has either been removed, like AppleScript, or been heavily sandboxed, like the JavaScript engine. Additionally, modern iPhones and Macs have PAC, or pointer authentication codes. These codes are made up of some of the previously unused top bits of pointers and special instructions set and check them in order to prevent code reuse methods like ROP, return-oriented programming. So if you have a function pointer that's overwritten on like the stack or the heap, those top bits will no longer match their expected value, and an exception will be raised when it's called from one of those special branch instructions. Finally, apps run in a sandbox with permissions restricted to only what the app needs to function. Access to sensitive content is often done through inter-process communication with more privileged system processes. And all these things in totality make it very difficult for hackers who really want to find a way to reliably perform arbitrary operations dynamically, ideally outside of any sandbox. And so we'll see that this is what NSPredicates are actually great for. So in order to understand a little bit more about the security on iOS, we're going to first have some background in Objective-C, which is the language that most of the user space code is written in. Though a lot of new code is written in Swift, there's still the majority of the shared libraries on the OS are Objective-C. So it's a superset of C with object-oriented programming concepts added in a way similar to Smalltalk. It's based on message passing, where methods are invoked dynamically at runtime by name. And these names are called selectors in the parlance of Objective-C. And so methods can be added and removed at runtime and have their signatures change. It's a very dynamic language. And it's also possible to access properties and call methods without arguments using strings concatenated with periods. These strings are called key paths, and they're going to be very important in the context of NSPredicates as well. So this is like the most basic hello world example, but it's actually got most of the elements we care about. So we can see there's this NSString, which is just the basic immutable string class, and we're going to call string by appending string on it. The method names are kind of weird because they have like that argument name within them. Just takes some getting used to. So we're calling that on the string hello with the argument world to get the NSString hello world. Then we use the key path string.uppercase string.utf8 string to get a C string pointer, which we can print with printf. And the ats in front of the quotes just make it an easy way to create constant NS strings. And similarly, other types like NS arrays and NS dictionaries can be created with the @ sign before brackets. All right, so we're 9 slides in, and I haven't talked about what the hell an NSPredicate is yet, so let's get into that. The Apple documentation says that they are a definition of logical conditions for constraining a search for a fetch or for in-memory filtering. This definition kind of sucks. They're just strings that are used to filter objects in arrays. So if you had like a student object, you might select students in array with a predicate like grade equals 7 or first name like Juan and age less than 16. These strings are actually format strings, so you can use percent escaped strings like %d to include a number that is passed to predicate with format in order to initialize an NSPredicate. And they implement NS coding, which just means that they can be serialized and sent over inter-process communication to other processes or completely remotely to other devices. And they are ubiquitous on iOS and macOS, first-party and third-party libraries and apps. NSPredicates are everywhere. To expand on the last point a little bit, we should discuss XPC. It's a common form of inter-process communication where one process can call methods on a remote object in another process. When XPC is used to call a remote method, the arguments are passed by the sender, and they're serialized, or archived, as it's known on iOS and macOS, and sent to the target where they are deserialized. It's common to see NSPredicate arguments used to filter the results of one of these remote calls in order to minimize the number of objects that need to be serialized by that target process and then deserialized when the receiver gets them. This is foreshadowing, just in case it was not already abundantly clear. It's going to be very important that NSPredicates are sent around via XPC. So here's just a small example of an NSPredicate in action. We're taking an array that contains some file names, and we use the predicate path extension equals pi to filter out the one that's Python. The resulting array contains that single entry, script.py. So that's just kind of a typical usage of an NSPredicate for just filtering arrays. So to get a little bit better understanding of what's going on within a predicate, the NSPredicate string is parsed by code generated with Flex in the Foundation framework. It's parsed into pieces called NS expressions and NS predicate operators. In this example from Code Colorist, a predicate named name equals Apple is parsed into 3 pieces, NS key path expression name, the equals NS equality predicate operator, and a constant value expression containing the constant NS string Apple. Yeah. The key path expression is also a function expression, so it can be further broken down into an operand self, showing that it acts on the objects being filtered, the selector, which is value for key, and the key path specifier, which is just name in this case. This is all a bit complicated, but it's not really necessary to fully understand this AST structure. More important for us is the question of what can an NSPredicate do? And the answer to that question is anything, sort of. It used to be anything. Now there's a big asterisk since Apple has taken many steps to make NSPredicates much less powerful, much less useful for exploits. In fact, nearly all the techniques I'm going to talk about today no longer work as they're being presented. Some of them work with some tweaks. Well, let's just take a look at NSPredicates as they were and at the limits of what can be done with them. So while at first glance, NSPredicates did not look interesting, they're actually a powerful scripting language. So as Code Colorist said in his blog post, eval, NSPredicates are essentially the eval function for Objective-C, kind of like the eval function in JavaScript or Python. So the scripting capability is due in large part to the function keyword, which allows any method to be called on an object with any number of arbitrary arguments. Code colorists also discovered that the cast keyword, just another expression in a predicate, this cast keyword could be used with class as the second argument to get a reference to any class, essentially functioning like NSClass from string, if you've done Objective-C programming. So an interesting thing is that this functionality is both intended and quite old. Function expressions were added in macOS 10.5 around the year 2007, which means they've been in iOS since the very beginning. So this dynamic code was possible this entire time. And this is just the official Apple documentation showing how to use function expressions, so it's not like they were a secret or anything. With the cast class trick, it was possible to use helpful classes like CN file services, which had this DLSym method to get the pack signed address of any exported function. So just to recap a little bit, that's the pointer authentication codes. We can get the correct upper bits using this DLSym method. And these addresses could be called with NSInvocation, which has a method invoke using imp. And that can be used to call the function with any number of arbitrary arguments. Effectively, now both the object-oriented methods of Objective-C we can call with the function expressions, and then we can use this trick to call any simple C exported functions without restriction. So this means that anything that could be done in an Objective-C program could be accomplished completely dynamically within an NSPredicate, completely sidestepping ASLR, codesigning, and pack. It was beautiful. So until now, the only predicates that we have seen have been like first name equals Swan. So it's understandable if you are very confused about how NSPredicates can be used as a scripting language. But it turns out the syntax of an NSPredicate is actually surprisingly rich and capable of representing all the concepts that we care about in a scripting language. First, we have variables and variable assignment using these $ strings. We have the function and key path expressions that we kind of briefly discussed to call any methods. Then there are these NSAggregate expressions, which are used to create arrays. But we can also use them to create series of expressions that will be evaluated sequentially, which will essentially form the lines of our script. Finally, subquery and ternary expressions can be used to create loops and conditionals, respectively. And so these can be used for control flow. Additionally, all the normal arithmetic and bitwise math operators can be used in NSPredicates, and we'll see this become very useful when we're calculating addresses using offsets later. So this is a Pi Objective-C script, so it's just like Python bindings for Objective-C that you can get. And this evaluates an NSPredicate script, and this script makes two variables, standard out, which is a file handle, and proc info, which is the process information. The objects are instantiated using the cast class trick that we talked about. And then it uses a ternary expression as an if statement, so that if the process name is Python, it prints out it's Python to standard output. All these expressions are wrapped in brackets, so they form a single NSAggregate expression, and each line here evaluates sequentially. So it's just a little example of how they can be basically used for arbitrary programs. So before forced entry, these NSPredicate scripts were essentially unrestricted, with the exception of predicates that were sent over XPC. These predicates were often limited using these things called NSPredicate visitors, implementations of a protocol where methods were used to check the components of an untrusted NSPredicate were safe to evaluate. These implementations use the expression type property of a NS expression to check whether an expression was a function or a key path. And if that were the case, it would only allow specific instances, only allow a subset of key paths or functions. However, without these restrictions, NSPredicates were basically arbitrary code execution, and they were used as such in forced entry. And now that we understand a little bit more about NSPredicates and their capabilities, we can understand the forced entry sandbox escape. So there was that crazy big JBig2 VM. It was used to create a fake object in memory that, when deallocated, evaluated an array of NS function expressions. These expressions cleaned up after the initial exploit, and it deleted the GIF that was actually a PDF. and crafted a second payload, another array of objects that was sent to the unsandboxed comm center process. These objects were chosen such that when the target deserialized them, it would immediately evaluate a new NSPredicate, which collected a bunch of device information before downloading and evaluating another NSPredicate payload that, again, could do anything after that. So after forced entry and the increased visibility of code color's earlier blog post, a few new restrictions were placed on NSPredicate objects. So there were these two denialists that were added, which prevented the use of a number of inherently dangerous classes and methods, with particular focus on classes and methods that allowed performing arbitrary method invocations and initializing arbitrary objects. They really tried to prevent initializing things that weren't expected. The class trick was forbidden, and calling class methods as opposed to instance methods on objects was also prevented. It's important to note, though, that these changes only affected first-party Apple apps and processes. NSPredicates evaluating third-party apps had this very small denialist of classes and methods. I don't even know if there were any methods. And they were essentially effectively as powerful as before. So only Apple was protected. So these differences were implemented with a single flag value called predicate security flags that was set for Apple processes when the class NSPredicate utilities was initialized. So this one flag is all that controls these higher security features. Here we can see one of the denialists of the classes, so it prevents the use of the class you see here. This is larger, and this is also kind of like the modern version, so it's quite large now. But it includes things like NSBundle, which is used to load other shared libraries, so to try to prevent you from loading other libraries, and things like NSCoder to prevent deserializing new arbitrary objects, again, trying to just prevent arbitrary objects from getting into your predicate. Additionally, Apple removed the CN file services DLSim method that was used both in NSPredicate and SLOP exploits, which is the selector-oriented programming. And it had proved to be super useful for attackers, so there's a reason they removed it. And they've been removing other instances of DLSim since then. Relatedly, the NS invocation class was also included in the forbidden classes list, and it generally they made it more difficult to use for exploits. They added this magic canary value and kind of changed the way it worked so that it was a little bit less flexible. However, we shall see that these denialists were way too small, and the fact that the security was enforced based on this single writable flag value made it incredibly vulnerable, incredibly fragile. The getValue method of NSValue could be used to perform arbitrary writes, overwriting any address with any desired value. This meant that the security flag could just be unset by calling getValue on the number 0 with the address of the security flag as the argument. Simple as that. Importantly, even though iOS has ASLR, libraries are slid by the same amount in every process, with the slide being chosen at startup. So if you had code execution in another process already, you could just calculate the values of any address using offsets. And there are many different ways to leak an address from within a predicate itself, so it's trivial to use an offset from a known address to find that flag address 100% reliably. Similarly, the lengths of the denialist dictionaries could just be set to 0, and then it'd be like they don't exist at all, removing any remaining forbidden elements. So all the techniques described in the previous slide can be seen here in this predicate, which disables all the security features that were added. So we can see that we use this hashtag self.hash to get the address of NSPredicate utilities. So when you call .hash on a class, it just returns the address of that class as a NS number. With this, we can see the offsets to get the addresses of the security flags and the lengths of the denialists. So they're just being calculated from offsets from that NSPredicate utilities class. And this is all being done from within the predicate. Once we have these addresses, then we can simply use that getValue to overwrite them, reverting NSPredicates to their fully unrestricted state. So here we also see what I call the MVP of NSPredicate scripts, which is non-retained object value. It's just kind of a way to take an S number and treat it as a pointer to an object. It's kind of like dereferencing a pointer within NSPredicate is how I think about it. And it can be used to access any class by reference when the cast class trick is forbidden. But remember, the cast class trick will be unforbidden once this is performed, so then you can just keep using it, which is nice. However, after a tweet of mine that may or may not have been influential, Apple added additional powerful restrictions, namely that the arguments of function expressions could not be pointer types. And they did this by inspecting the method signatures, which are strings of characters representing the types that a method uses. The caret and the question mark types refer to data and function pointers, respectively, and they were forbidden in processes with that high security flag set. In predicates, in NS function expressions particularly. However, they overlooked the asterisk type, which refers to character pointers, refers to C strings. I don't know why this type exists in the first place, since it should just be encoded caret C, but it worked out for us here. This means that we could simply achieve the exact same kind of arbitrary right that we had before, but now we just use get C string instead of get value. So this predicate accomplishes the same thing as the previous one shown. However, it uses the function setDebug predicate security scoping, it's kind of a mouthful, to unset the high security flag after setting our internal release type to 3. So this is a trick that's necessary because the predicate high security flag was moved from a static address, static offset, to the heap. So it was harder to find. Luckily, NSPredicate utilities just gave us this nice convenient method to unset it regardless. Again, from here, the predicate can be used to fully script Objective-C just as before, just like before there were any security features added. This is that setDebug predicate security scoping method, which could unset that high security flag, now stored at CF predicate policy data plus OX30. But only if that OS variant has internal content function returns true. And this is what we accomplished by setting the internal release type to 3 in the predicate. That allows us to have this function return true and allow us to unset the high security flag. So while I've demonstrated how to get around the limits that Apple placed on NSPredicate, I still haven't shown how to call arbitrary functions now that they've removed that DLSim gadget. Luckily, there is still at least one more signed reference to DLSim that we could get, and that's using this DLSim func method of a class in DVT Instruments Foundation. It's just kind of like a developer tools library. So this address could be used with apply function info, a method of RB stroke accumulator. So that's a method, a class in RenderBox framework to call DLSim and get the zero context signed address of any exported function. In turn, these signed addresses of functions could be also used in that apply function info method with up to 4 arbitrary arguments or more arbitrary arguments if it was OK not to have control of that 5th argument, which would become the function pointer. This effectively bypasses PAC, as even though it's not possible to sign arbitrary pointers, which is generally what you want from like a full PAC bypass, the combination of the scripting capabilities of NSPredicate and the use of any exported function is basically more than enough to accomplish anything that you want to. And this is that apply function method. We can see that it uses this BRAAZ instruction to call the function pointer passes the first argument. This is an instruction that authenticates and calls pointers signed with 0 context values exactly as we need in order to use the reference to DLSim and the values, the function pointers that DLSim returns, which are also that 0 context signed. Putting all the pieces together, this is an NSPredicate that calls nslog on iOS 16.3 after removing all the mitigations protecting Apple processes. It's like probably very difficult to see, but the point is that it's complicated, but it's still possible in iOS 16.3 beta to do anything with NSPredicate using these techniques. All it takes is some creativity, some knowledge of Objective-C, and the useful classes that are already defined in the shared libraries of iOS. Now that we can do anything, again, within an NSPredicate, similar to what was possible before forced entry, there's only one potential impediment to exploiting processes that evaluate NSPredicates, and that's NSPredicate visitors. So the most surprising thing I found in my research was that it was possible to just say no to nearly all NSPredicate visitors. Each daemon implements their own version of this protocol in order to only allow those expressions in predicates which it expects to be in a normal NSPredicate argument. It uses the expression type property to check what kind of expression each component of a predicate is, so that simple expressions like constant values can just be allowed, and other more dangerous ones like function expressions can be forbidden or limited. So like a lot of them have like a set of selectors that you're allowed to use in function expressions, or a set of key paths that you're allowed to use. However, the expression type was just this integer that was read directly from the serialized data sent by an untrusted process. This means that setting every expression type to 0 in a malicious NSPredicate led the receiver to interpret it as only containing constant values, bypassing any additional validation. So it never saw that any of them were function expressions, so it never checked to see what functions they were. So here's an example of a NSPredicate visitor implementation for photo library queries. So we can see here that it uses that expression type property to decide whether additional checks need to be made on each expression that it visits. So like it checks to see if it's a key path expression using these bit operations, and then checks the key path. And then here we can see at the bottom that the only implementation of expression type, the getter for this property, was something that simply returns the number stored at the offset 16. And this number is taken directly from the archive data in NSExpression init with coder, which is that method that does the deserialization. And we're going to see that here. So this XML on the right is the serialized representation of an NSExpression, the one to the left. So we can see that, and hopefully you can see it, that the expression type is just an integer within this XML. So you could just set that to whatever you wanted, and it would say, OK, this is a 0 type, so it's fine. With this bypass, processes that were otherwise protected by NSPredicate visitors, in addition to the standard first-party NSPredicate mitigations, were now vulnerable to 100% reliable arbitrary code execution. Apps and processes that were vulnerable included CoreDuet-D and Context Store-D, which aggregate user behavior data on the device. App Store-D, which can install new applications. OS log service, which can read any of the process logs. And Springboard, it's kind of the home app, similar to Explorer.exe on Windows. And it has many different sensitive permissions. I feel like I said that. Just more. So by exploiting these vulnerable processes, a malicious app could gain access to location data, message contents, and even install apps potentially on the target and maybe paired devices as well. So lots of sensitive permissions, sensitive entitlements these processes contain. So it's pretty simple to find XPC service clients that send NSPredicates like this one. This one's a CD interaction recorder. Just by grepping the Objective-C headers. And that's a great thing about reversing Objective-C libraries and apps, is that they must contain this header information because of the dynamic dispatching of methods. Because they have this dynamic runtime, they need all this information. And so there are tools to extract all this header data. Here we see that many methods take an NSPredicate argument, and this predicate is sent to that CoreDuet-D service. This is just a little free script which, when attached to a process with the entitlement to communicate with CoreDuet-D, sends an NSPredicate that will cause it to crash on access to AAAA, just a simple crash POC. It uses the method count contacts using predicate error, which takes a predicate argument and sends it to CoreDuet-D. And before calling this method, the function expression has its expression type set to 0, so that it bypasses the NSPredicate visitor that CoreDuet-D uses. Similarly, this script attacks the OS log service, XPC service. Every app can communicate with this service, so it can be directly exploited to gain access to arbitrary logs, potentially with sensitive information, or it can just be used as a way to have code execution persist outside of a malicious app after the app is closed or deleted. On the iPad, any app can communicate with the Springboard XPC service that determines which app scene should be used for handling different events. This is done using an NSPredicate provided by an app. The predicate is validated using this UI target content identifier predicate validator class. So it's an implementation of an NSPredicate visitor. However, like the others, it relies on this expression type value to determine whether expressions are safe. And that means by using a malicious NSPredicate visitor, we can take any NSPredicate and use the visitor to set all of its expression types to be 0, which will denote the constant value. So that's what this NSPredicate visitor does. So this is the actual predicate that we're going to use to exploit Springboard in a second here. First, it uses the getCstring method to perform the arbitrary writes necessary to clear the deny lists and set the internal release type to 3 before calling setDebug predicate security scoping. That unsets the high security flag. Finally, it uses NSFileManager, which previously was a forbidden class, to copy the contents of user notifications to the crash report directory so it can be easily copied off the device. In a real scenario, they could be zipped up and sent over HTTP to a server that an attacker controls. There's lots of different classes for doing those sorts of things that we could get access to. The predicate then accepts our evil NSPredicate visitor, which sets all the expression types to 0 in order to evade the NSPredicate visitor in UIKit core. And finally, the predicate is assigned to the scene activation conditions, which is what sends it to Springboard to be evaluated when an event, like opening the app using one of the shortcuts, is generated. OK, so I never took my iPad out. Sorry about that. It's supposed to be a live demo. Should have set it up beforehand. All right, but I guess I'll talk about it while I try to do this. Oh, I got to take off this thing. The computer only has 2 ports. Stupid MacBook. All right. So we are going to be exploiting that Springboard vulnerability on an iPad using that predicate that we saw to copy all the user notifications to this computer. Again, in a real scenario, it would probably be sent over like HTTP, but it's gonna work. Come on. Sorry. Gotta wait for QuickTime to work. Sorry. All right, I'm going to keep talking while I try to set this up. We have the, like we saw before, we have that predicate visitor, which is going to set the expression types to 0. No. OK, well, I have a video of the demo, so I guess I'll just show that. Sorry about that. So this is the malicious app being loaded. So we can see our notifications here that we have the iMessage that says this is a secret. And then we are going to open up our malicious app, which sends those notifications over to the left there, where we have a script waiting to receive them. And we can see that it gets that notification information. Thanks. Thank you. Sorry for the technical difficulties. So, conclusion. So how should app developers use NSPredicates safely? If you went by Apple's developer documentation, you might think that they're not dangerous at all. There are no warnings anywhere in any documentation that they should be handled with care. But that's wrong. Put simply, if you can avoid them, you should avoid them. Sometimes it's not possible, like if you're using core data. But where possible, use block predicates instead of string-based predicates. Never use an untrusted string in predicate format or with the key path format string. Don't unarchive and evaluate untrusted NSPredicate objects. And any predicate that has been unarchived should probably be considered untrusted from a file or over the network. And don't use any dynamically allocated strings for the format string, as that could just take a simple heap overflow and turn it into an 100% reliable arbitrary code execution just by overwriting that string. So luckily, for the security of iOS and for macOS devices, Apple's finally begun to limit NSPredicates in a way that is less easily bypassed. The return and argument types of function expressions must be objects, even in third-party apps, and there's no flag that can be overwritten anymore to change this. NSPredicates could still be used by malicious apps to bypass any kind of meaningful App Store review. As far as I know, there is no review to make sure there's no downloading and evaluating of dynamic NSPredicates. And in fact, this behavior actually occurs within their own apps and libraries, so you would think they'd probably get rid of it there first. However, a lot can still be accomplished with these NSPredicates, even in a context where you don't control the entire environment. And this is unlikely to change until Apple fundamentally alters the behavior of function and key path expressions. Until then, they're basically landmines scattered everywhere, waiting to explode and destroy the effectiveness of all the amazing security features that iOS has. For now, they remain Apple's predicament. And that's it. Thank you.